so hard. If only I knew somebody who could help.
Hey, you know what? We shouldn't put any graph.
This is the NYB Help Squad. Please state your name and your emergency.
Hello? Yes, my name is Tony, and I'm in the physics lab, and I really don't know what to do with this.
We're on our way. Hi, I'm Dean.
I'm Lauren.
I'm Kai, and we're the NYB Help Squad.
What seems to be the problem, Tony?
I have this lab, electric field map. I don't know what to do. Can you please help me?
It's alright. We're here now. We're going to explain the lab, we're going to show you what to do. And then, you're going to do it yourself. Because that's how learning happens. Before we start, let's go over the basics of electric field mapping. An electric field is actually very similar to a gravitational field. For instance, the strengths of both these fields decrease as the distance between the objects in question increase. Furthermore, particles placed in both electric and gravitational fields will also experience forces. However, the difference lies in the fact that a gravitational force acts on a mass, while an electric force acts on a charge. In fact, the formula for an electric field is E equals F over Q. The unit of E is in newtons per coulomb, as it is defined as the electric force in newtons on a charge in coulombs. Additionally, the force originating from a gravitational field will always be attractive, whereas that from an electric field can be attractive or repulsive, depending on the charge it is acting on. Since an electric field always emanates from a positive charge, a negative charge placed in the field will flow in the opposite direction. When another charge is placed near the first, the lines will curve towards or away from it, depending on the sign of its charge. By the way, electric field lines can never cross, but they are crossed by equipotential lines, which are actually perpendicular to the electric field lines.
Equipotential lines are exactly what they sound like, lines of equal potential. These lines of equal potential or voltage will surround a charged particle in a circular field or rings. The equipotential lines and the charges they are surrounding can be thought of in the same way as a topographical map of a mountain. The lines closest to the charge will have the highest altitude or potential. As we travel down the mountain, the lines furthest from the charge will have the lowest altitude or potential. A charge located in this equipotential field will therefore have an electric potential energy. By locating all the points with same potential, an equipotential line can be mapped. In this experiment, we will sketch the equipotential lines first, and then simply draw the intersecting perpendicular electric field lines.
The following materials are required to complete this lab: 2 wires with magnetic leads, 2 banana wires, an optional meter stick, a digital multimeter, a grid sheet, a metal conducting sheet, and a DC power supply. To start, connect both magnetic lead wires to points 7 and 21 respectively. Next, plug both ends of the wires into the positive and negative sources of the power supply and turn it on. Verify that the power supply has an output of 10 volts as listed. By using one of the leads as a probe, it can be seen that the potential difference decreases as the probe travels from point 7 to point 21. Eventually, as the probe touches point 21, the potential difference will be read as 0. Halfway between both points, the reading on the multimeter should be approximately 5 volts. Let's do an example by mapping the 7-volt equipotential line around the first charge. Start by locating the first point near the charge that reads 7 volts. Next, Carefully move the probe until you find another point with the same reading. Keep on doing this until you have enough points to complete a 7-volt equipotential line around the charge. Having mapped several equipotential and electric field lines, you'll get a drawing that may look similar to this. The 7-volt and 6-volt equipotential lines around the positive charge, the 2-volt and 3-volt equipotential lines around the negative charge, the 5-volt midline, and the electric field lines.
Thanks for your help, Dean. I really appreciate it and now understand it.
No problem, Tony. If you ask me, you have a lot of potential.